Okay, guys. All right. So I'm just wanted to go through some of these Google slides on work. Now, I know it says work, power, and efficiency. I'm just going to go through the work part right now, not the power and efficiency part. We'll do that later. Okay. So anyway, so here we go. And next slide. Oh, yeah. Okay. There's all these animations on here because Mr. Leonard did this, and whatever, he likes stuff like that. Okay. All right. Work. You don't need to get the definition of power or efficiency, but you should know the definition of work. Hopefully, you watched the other video that I did in front of the chalkboard before you're watching this. So you should have that. But work is caused by a force. All right. And the force either gives the object energy or it takes energy away from the object. And it's measured in joules. Okay. All right. Here we are again. The definition: work is defined as a change in an object's energy. Okay. All right. Work is done when a force acts on an object. Okay. And it depends on the direction. So if the object does not move in the direction that the force is applied, then no work is done. Okay. So, and again, all right, so here's the first equation. Work is force times distance. That's a simplified version of it. And actually, I didn't do that. Leonard did that. All right. It's actually not distance, it's displacement. Displacement is a vector. Okay. The direction counts. Okay. And here's a good example of that, just to show you this picture. So you got this guy who knows what the heck he's pulling here, but he's pulling some sort of device. But you can see that, and this is why the angle counts. So you see like the force is transmitted through whatever this handle is. All right. So the force is actually going up in this direction, which means only this x component of the force, if you draw a triangle in your mind, the x component or the cosine component is actually going to make the object move. This upward component right here is just wasted. Okay. It's not, it doesn't contribute to the physical situation. That's why the cosine term is there. Okay. And you can remember a cosine is a maximum, all right, at 0, and it's a minimum at 90. So if this guy were to lower or squat down a bit and then try and pull it so that handle was parallel to the ground, he would more and more of his force would go into pulling it, and less would be wasted. All right, and that would mean if they're parallel, that the angle between the force and the displacement would be 0. And again, if you were to try and lift straight up and try and get it to move sideways, it wouldn't work because the angle between the force and the displacement would be 90 degrees. Okay, oops, and I got to go back here. All right. Okay, so there's the equation again. And here are your various work equations. Okay, and again, this is really all one equation. It's really W equals delta E in various forms. Obviously, as you're doing a problem, if you see the word force, if they give you the word force in it, then you're probably going to use this version. If you see an object being lifted or an object being dropped, you're probably going to use this version. If you see an object being speeded up by a force or slowed down by a force, you'll use this version. And if you see an object changing height and speed at the same time, you're going to use both of these, okay, together. So there you have that. Okay, here's just some pictures. All right, here's work being done by a rocket engine. So since it's accelerating the rocket, it's giving it kinetic energy, and it's also giving it potential energy. So I would use the last version, the one with the two types of energy in it, in order to solve that problem. Okay, so here we go. Here's a change in potential energy. This guy right here, obviously that's a change in kinetic energy. All right, and again, the energy comes from various places. In this case, going up the stairs, or this guy sprinting like that, the energy is obviously coming from the person's internal respiration, which came from the food they ate and so on. Because remember, energy can't be created or destroyed, but it can only change form. Okay, and when energy changes, we say that work is done. Okay, gravity does work. All right, obviously, if you drop an object, it changes an object's energy. Okay, so and this dam here is a good example of how human beings have used the concept of energy stored in gravity for a long time. So you back up the water here, and then what happens, you allow some of the water to fall through tubes in the dam, and then they hit generators, okay, and so on. And that then energy is converted into electrical energy. Well, where did electrical energy come from? Well, it came from the work that gravity did on the water that is being backed up by the dam. Okay. Uh, okay, this is important, and there's some language here that's important. There's a concept of a conservative and a non-conservative force. All right, a conservative force is one in which it doesn't matter the direction. The only thing that matters in the energy change are the two endpoints. So here's the water starting. Here's the water down there. We say it has potential energy up there. We say it doesn't have down there. Okay. And again, or another way to look at a conservative force is any energy you put out of it, if you bring it back to its original position, you'll get the exact same energy back. So if I take a cup of water and I bring it up to the top there, and I gave it potential energy, let's say I gave it, I don't know, 100 joules of potential energy, bringing it up there. If I bring it back down, gravity took exactly 100 joules away out of it, okay? And no more, no less. So we say gravity is a conservative force, okay? Friction, on the other hand, you don't get the energy back. So if I take this block and I move it over here, friction opposes the block moving. If I move the block back to its original position, since friction changes direction and poses it in the other direction, I don't get that energy back. With gravity, if you put energy into it, you get that energy back, or gravity will give it back to you. That's why we say it's conserved. It's a conservative force. Friction is a dissipative force. It dissipates the energy. So if I move this block this way, the friction did work against the block and it dissipated. If I move the block back to its original position, I didn't get that energy back. Friction took it away again, and there you have it. So friction, we say, is non-conservative. Okay, and there's the definition of those things. Okay, all right, that's it for now. So let me get out of here. All right, and it takes a second. Come on now. There we go.